So since this is an early worksheet, I'm going to try to help the people at home with it too, okay? So people at home, here you go. From the motion map, now this worksheet is on Google Classroom, all right? So it's a worksheet for you on Google Classroom. I'm trying to talk to you about it. From the motion map above, answer, what can you conclude about the motion of the object? One, its velocity is constant. Not only are these arrows the same length, but you can also see that the dots are equidistant, right? So this motion map, whatever it is, it's going to constant velocity. B, draw a qualitative graph. Now qualitative means it doesn't have numbers on it, but it looks right. That's what qualitative means, all right? So if we're going to draw a qualitative graph, and we're going to say, oh, well, it starts at distance 0 and time 0, then any straight line that you draw on here is perfectly correct. It could be steep, it could be flat, because there's no numbers on it. But what's important is that this line is straight. Because if this line curves, then that car would be accelerating. And that's something we'll talk about more tomorrow, or you'll see on lawnmower tomorrow. And then now, just like from early in class, if we're drawing a qualitative graph of that car, just a straight line like this. Does that make sense? So, check this out. And this is going to help you with the back of the page, which I'm not going to do a video on. But if this car was going at a constant speed, and then a couple seconds later, it started going at a lower velocity, then the graph would look like that. Does that make sense? And then if it stopped, the velocity would go down to 0. Everybody feeling that? So these are some funky graphs that you may not have seen before. That's what I'm trying to work your way through. Describe the area under the curve. Oh, E. Write a mathematical expression that represents the relationship between V and T. And if that confuses you, you're trying too hard. How about this? Velocity is equal to distance divided by time. That's all they're looking for. Describe what the area under the curve represents. And this is a topic I haven't covered yet, but it's really easy. Ready? If we go up here and we do our original problem, the cars that's speeding up, the cars that's slowing down, it's going a constant velocity. Let's say that this is meters per second. 1, 2, 3. So this is velocity, and this is time going by. Right? So the time would be 1, 2, 3, 4, 5, 6 seconds. Is everybody following me? So if the car is going 2 meters per second, remember this is meters per second, for 6 seconds, we could write a formula, V is equal to D over T, and we could say if it's going 2 meters per second, that's equal to distance over 6 seconds. 6 times 2 is what? 12. So we know the car would have gone 12 meters. Take a look at this graph and tell me where you can find the number 12 if you look at this graph that you made. Because you're going to be able to apply this principle to future graphs. Like the back side of the page, maybe even. That's right. If you look at a velocity over time graph, the area under the line is equal to the distance traveled. That's like a derivative of this equation. Does that make sense? You can derive the distance by just looking at the area. And here's a way you can think about it. This shape makes a rectangle. And this rectangle is 2 by 6 in my made up one. What's 2 times 6? 12. So the area under the line on a velocity over time graph is equal to the distance traveled. That is a note that you will need to use for the rest of this chapter. Describe what the area under the line represents. That's the distance. Merry Christmas, everyone, and Happy New Year.